Find the equation of the plane through the points P, Q, and R with coordinates shown. So we have 3 points and 3 non-collinear points in space will determine a unique plane. The equation of the plane in space will be a first degree equation, ax plus by plus cz equals d. And the normal vector to the plane is given by the coefficients of x, y, and z. So n equals abc. And then to find d, once we have the normal vector, we can use any one of the 3 points and plug it in, and that will tell us what d is. So we need the normal vector to the plane, and when you have 3 points, then you can create a normal vector as follows. You can make the vectors from P to Q and from P to R, and then the normal vector will be perpendicular to both of those. So to create a vector that is perpendicular to a pair of vectors, we will use the cross product. So our normal vector will be PQ cross PR. And we could have used other vectors here as long as we use these points P, Q, and R. We could have used QP and QR, for example, or RQ, RP. But PQ, PR is fine. So the vector PQ is the vector (4 minus 1), -1 minus 4, -7 minus 9. And the vector PR is 5 minus 1, 0 minus 4, -3 minus 9. And just to make our calculations a little bit simpler, we could scale this vector down since each of the components is a multiple of 4. So instead of saying that our normal vector is PQ cross PR, we'll say that our normal vector is PQ cross, and we'll do 1/4 of PR. 1/4 of PR is 1, -1, -3. No need to work with unnecessarily large numbers. So we have to make this cross product between PQ and 1/4 PR. So that cross product, 3, -5, -16 cross 1, -1, -3 is obtained by doing the determinant of a 3 by 3 matrix. We'll put I, J, and K up top, and then we'll put P, which is 3, -5, -16, and the 1/4 PR, 1, -1, -3. And the determinant of this matrix, going across the first row and doing a Laplace expansion about the first row, is what it's called. It's I, the vector I, times the number, which is the determinant of the 2 by 2 matrix that is obtained by removing the row with I and the column with I. So this 2 by 2 matrix down here. So the determinant of the 2 by 2 matrix A, B, C, D, the determinant of that is AD minus BC. So -5 times -3 is 15 minus -1 times -16 is 16. And then we go to the next entry in the first row, and that would be J, and we have a plus minus plus effect as we move across the first row, so it's going to be minus J times the determinant of the matrix obtained by removing the row and column that J is in. So that would be this, the 2 by 2 matrix, 3, negative 16, 1, negative 3. So let's just keep that in mind here. 3 times negative 3 is negative 9. And then minus negative 16 times 1 is negative 16. So that's going to be minus negative 16 or plus 16. And then we have plus k times the determinant of the 2 by 2 matrix that we see here, which is negative 3 minus negative 5, so negative 3 plus 5. So our normal vector is I times negative 1, or negative I, and then minus j times 7, so minus 7j, and then plus 2k. Or in the form that we were using here, negative 1, negative 7, 2. So that's our normal vector, and therefore the equation of the plane looks like negative 1 times x minus 7 times y plus 2 times z is equal to a number d. And then to get that number, we can use any one of the 3 points that was originally given. So let's look at the point P. What were the coordinates of P? The coordinates of P are 1, 4, 9. So P was 1, 4, 9. If we plug that in, if we plug in 1, we just get negative 1. Plug in 4, we get minus 28. Plug in 9, we get plus 18, and that's D. So negative 28 plus 18 is negative 10, minus 1 is negative 11. So D is negative 11, and our plane is negative x minus 7y plus 2z equals negative 11. And if we want, we could multiply this through by negative 1, maybe make it look a little nicer. X plus 7y minus 2z equals 11.